Well, hello, good morning, team. Chemistry Coach coming at you. We are going to continue the video we started with the other day on liquid properties and vapor pressure and all that fun stuff because we ran out of, well, I guess I could do, 2-hour videos if you want, but I can't focus that long. I remember when I was a student, I'd be like sitting in my classroom and about 10 minutes into it, I'd be off daydreaming or talking to someone. I can't say I was the most ideal student sitting in class, but I had focus issues. That's okay. We can still get through it, and you can still get your A's, right? All right. So we were looking at vapor pressure curves, right? Looking at, molar heats of vaporization and boiling versus evaporation, all that fun stuff. So let's take a look at that vapor pressure curve. And remember, where that vapor pressure curve came from is we took data from a vapor pressure table, right? This happens to be for water, so you get all the different temperatures, and you can see as the temperature goes up, the vapor pressure goes up, right? Nobody wants to read this. I guess in lab, if you know the specific temperature, you can figure that out. But if you're in between values, then you got to do linear interpolations and all this garbage. The ideal goal for a chemist is to get an equation to represent all of that. Publishing that, not fun, right? Even you can plot it, and plots are nice, but a lot of people don't like reading off of graphs either. So the ideal way is to get all of this information, all of that vapor pressure data, wrapped up into one nice, concise, beautiful mathematical equation. Yay, us scientists, right? This is a driving force for a lot of science. And you see a little bit of this back in my video last semester, one of my lab videos where I talk about graphing data. And the reason we like to do that is to be able to get a mathematical equation to represent that particular plot. Hey, and once you got that mathematical equation, right, you can just calculate, hey, what's the vapor pressure at this temperature? What temperature would give you this vapor pressure? And you just pop it in the equation, you're good to go. Well, we're going to do a specific aspect of this, but the process I'm going to go through, I'm going to derive this for you today. The Clausius-Clapeyron Equation. Of course, I just call it the clap. Hey, we got the clap. But I probably shouldn't say that on video, right? So the clap equation, making fun of me, you'll never forget it, right? We're going to, this is a specific application of the general process we're going to show you. What do I mean we? I'm going to show you in the next few minutes how to take data tables, make plots of them, and then try to get a mathematical equation from that plot. Yes, that is a driving force for a lot of lab work we do. Pay attention, mosquito. So the Clausius-Clapeyron equation is a specific equation used to represent the information on a vapor pressure table and curve. So we've seen these before. That's in the last video. And again, we can use this to kind of eyeball values, right? So we could say, hey, you know what? If I'm at this temperature, get your nice ruler or something, or if it's on a computer, you can get the straight line. So you can just go up and over, and you can connect things. And if it's on that particular curve, that happens to be the boiling point, right? So if you're at some particular atmospheric pressure, you look over and go down, and that's the boiling point. Or you could say, well, if I want, what would be the pressure if I want it to boil at some particular temperature. You can just go up and over and go, well, that would be the pressure necessary. And you can see how the boiling point decreases with pressure. We talked about that qualitatively in the last video and looked at it briefly. But as the pressure's dropping, you can see that boiling point is also dropping. So the vapor pressure curves are wonderful. You can eyeball things from it, especially boiling points. You can see trends. The problem with this beautiful graph, if it's not a straight line. Scientists like straight lines. We could get a mathematical equation to represent that, but it's not going to be a pleasant one. We could, right? But we like happy math, simple math. And what's the most famous equation you probably learned in algebra, other than the quadratic equation, right? Y equals mx plus b, the equation of a straight line. That is what we're after. And you're going to see this trend through a lot of chemistry and other sciences. You're going to see equations given to you. A lot of times those equations come from plotting two variables and then rearranging this. See, this is not straight, right? I want to make it a straight line. So what you do as a scientist and go, maybe have a hot dog at lunch or something, talk with your friends, and go, how can we manipulate these variables? In this case, pressure and temperature, but it could be any two variables. How can we manipulate those mathematically to get that into a straight line? Right? I'm not going to go through the tricks for that at this point. But we've got logarithms, natural logs, base 10 logs. You can do inverses, you can do squares, square roots. There's a whole bunch of different things. So you just kind of, dork around with it until you get a straight line. And once you have that straight line, you can do a least squares fit. You can do it by hand. Is not fun. You need a statistics class for that. But you can just pop it on your computer, right? Look at my graphing stuff, videos, and you just, click on, add trend line, and pop. There's your y equals mx plus b. It's great. And the computer gives you the slope and y-intercept and stuff. We'll look at that specifically in the next board. But what we want is a straight line. Now, specifically for this, because that's curve, see the exponential part of that? We need to get a logarithm to get that into a straight line. So what they ended up, give you the answer ahead of time. So they said, or found, if you take the natural log of that pressure, and if you plot it versus temperature, you still don't get a straight line. But they found if you plot it versus the inverse temperature, of course, temperature is going to be in Kelvin here. And you can do this in atmospheres, millimeters, mercury, whatever works. But if you take the natural log of the pressure and plot it versus the inverse temperature, what do you get? You get a straight line, my friends. Yes, victory lap! Ha 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 ha. And then we can do a least squares fit and get y equals mx plus b. And we can get an equation to represent that straight line. Yay, that's what we're after. So what I'm going to do is erase this, get a new board. Let's take this particular plot now. That's the one we're interested in. We can do it for any species, right? We could do it for water, for ammonia, for methane, and they all look like that. They're just shifted back and forth a little bit. Slopes vary a little bit based on the molar heat of vaporization, we'll see. But let's take this and see how we can extract information to get this wonderful Clausius-Clapeyron equation. I'm going to erase all this. Be right back. You ready for this? This is used a lot in science. Remember this, so if you move on to a master's degree or do like a senior level undergraduate research project or a PhD or something, you may end up doing this, right? You're just going to get a slightly different value for something. All right, so we've altered, remember we've got our data. We look at two variables and we can plot the mathematical relation between them. If it's not a straight line, you go, crud, I want a straight line. Right? My horrible accent there. So in this case, we did the natural log of pressure versus inverse temperature. That may take several tries, right? You got to play around with it and go, that didn't give me a straight line. That didn't give me a straight line, right? And the longer you do it, the little tricks you learn, you start to see trends. So we do a least squares fit. Why are we doing that? Because we want an equation for a straight line. And my algebra people, you know that's y equals mx plus b. So let's look. So we are going to take this least squares fit and that equation for a straight line and create an equation for it specific to those variables. And then we can use that equation to represent in this case, the vapor pressure data table, the vapor pressure curves, and we could calculate the pressure at any temperature or boiling points at any pressure, all those great things. And we can avoid the graphing and plotting, but we got to do it once to get to the equation. This is the key. All right, let's take a look at what these variables are. Y is the y-axis, okay? So the pressure depends on the temperature. That's the dependent variable. All right, so let's put dependent variable. This is all on my graphing video, right? So if you look back in my videos for through my labs, you'll see what I'm plotting. X is my independent variable, right? So the y-axis depends on the x-axis. So X is my independent variable. Just a little review here. And then we will end up deriving the Clausius-Clapeyron equation. And then we'll do an example for it to show you tracking the uncertainty is not so fun, but it's not too terrible mathematically. What is M and what is B? Well, my algebra people, tell me. M is the slope. And you can see we've got a negative slope, right? And B is the y-intercept. Let's do that down here. Y-intercept. So if you're on a computer, the computer will give you the value for the slope and the value for the y-intercept. So then all you have to do is plug in any, in this case, inverse temperature. You can solve for the log of the pressure and then take, e to the base of that and you've got the pressure. Or you can take any log of P, solve for 1 over T, inverse it. You can solve for the temperature and the boiling points if you want to at any particular pressure. Very, very useful. But let's put some things in. What we're after is M and B. What does that represent? Is there a property, in this case of a liquid, that represents? Well, what is one of the main properties we looked at that represents, right? Looking at a liquid and the forces that hold it together, and you're trying to rip those particles apart. What determines that? Molar heat of vaporization, right? Oh, so I wonder if maybe that slope is representing, that value represents somehow the molar heat of vaporization. It does, by the way. Okay, anyway. So what this will end up looking like, y is the log of P, right? That's the y, correct? M, turns out it's negative, right? Negative delta H vaporization over the universal gas constant. Ha ha ha. So that's what M represents. That's what we're after typically in a lot of science experiments. It's like, what does the slope represent? And then, boom, we get an equation from that. X is the inverse temperature. And then the y-intercept is an issue. All right? So you can start to see this equation starting to form. The issue with this is that y-intercept. That's an issue. So what we're going to do is a neat little trick on the next board. We're going to get rid of that. All right? What we're going to do is we're going to take this equation at one temperature and pressure, so P1 and T1. And then we're also going to take this exact same equation at a second point, like an initial state, final state. Initial state, initial pressure P1, initial temperature T1, and then we'll take it again to another state, a P2 and a T2. And then we're going to subtract those two equations. And you're going to see, since this is a constant, right? That's going to cancel out. Yeah! So let's do it. Let's derive the Clausius-Clapeyron equation. Be right back. Hey, if you are feeling strong and smart, not that strength has any, the strength of mind, right? Do that for me. Get this equation at a P1, T1, and write it again at a P2, T2. Okay, we're also going to assume this is constant. This whole term. So the slope, the y-intercept, we're going to assume are constants. You'll be able to factor this out, and you can get an equation by subtracting these two. Go for it. See if you can do it. Test yourself. Here's our setup. You ready? Normally, I just skip this step when I'm doing it, right? But I want you to do it. I'm going to go through it slow the first time because we will be doing this again several times this semester. And you're going to see several equations that look identical to this, just instead of the delta H vap, they'll have something like an activation energy or something there. All right. So for our initial state, P1, T1, let's write that equation from the y equals mx plus b. So natural log of P1, negative delta H vap over R, 1 over T1 plus B, the y-intercept, which we don't know. For the final state, P2 and T2. Natural log of P2 is negative delta H vap over R, 1 over T2 plus the y-intercept. Boom! Right? Let's now subtract. This is the trick. Subtract these two equations, right? Final state minus initial state. Okay? And we're going to do that to eliminate this constant B. Bye-bye. Then we don't have to worry about it. B for bye-bye. And then we'll derive the Clausius-Clapeyron equation. So I'll talk about it. We'll do it on the next board, but you're going to take the final state minus initial state, right? So you can take log of P2, natural log of P2, minus the natural log of P1 equals this whole term at state 2 minus that whole term at state 1. You're going to see that the b's cancel out. You can factor out this constant, negative delta H vap over R. You can do some stupid log tricks. I'll give you that hint ahead of time. You ready? So here's the logarithm trick. There's going to be several logarithm tricks we're going to be using in this class. Logarithms. Still hurts my brain thinking about logarithms, but there's some really neat tricks in there. You ready? Log of A minus log of B is log of A over B, right? That's one. It's what I call the silly log or stupid log tricks, right? That's one of them. So you'll see this log of P2 minus log of P1, right? You can do this. All right, let's get this on the next board. All right, here's your setup, right? Final minus initial, so log of P2 minus log of P1 equals final minus initial, that whole term minus that whole term. Good so far? So let's do our stupid log trick, right? So log of A minus log of B is log of A minus B. So this will be the log of P2 over P1, right? I'm going to leave this term as it is, but I'm going to do some tricks with this negative sign to help you see that B. You can probably see how the B is going to get eliminated. You have a positive B here, and the negative factors through for the negative B. Let me draw that out. I'm just going to do this once. So let's do the negative delta H vaporization over R, 1 over T2 plus B. And I'm going to leave this as negative delta H vap over R so I can factor that out later. Right? So this will be minus negative delta H vap. That was an ugly V. Over R. All right? Times 1 over T1. And let's bring that negative sign through. So we get a minus B. So I just kept this term together and left that negative sign there, but I carried the negative sign through there and made the minus B. So hopefully you can see these B's are going to cancel out. You see that? So those go bye-bye. And then I'm going to factor out the negative vap over R. So let's have at it. You ready? So log of P2 over P1. You see the equation developing here? Just steps of mathematics. Let's factor out negative delta H vaporization over R. The B's cancel. Then you get the 1 over T2 minus 1 over T1. That, my friends, that's one. I've seen a different form for this. This is the Clausius-Clapeyron equation. And that's all Clausius and Clapeyron did. They got, and you can do the same thing and name it after yourself if you want to. Whoop, whoop. Another way that I've seen, the way I learned this when I was a student, is they got rid of the negative sign here. So what they did is they switched the temperatures. Right? So you might see this. Log of P2 over P1 equals positive delta H vaporization over R. You factor the negative sign through, and you get 1 over T1 minus 1 over T2. Right? Either one of these is fine. I learned this one when I was a student, so it's stuck in my brain, but I prefer this one because you're doing the final minus initial, right? T2, 1 over T2 minus 1 over T1 makes more sense, but some people don't like that negative sign out in front, so they just factor it through. I don't really care. But do you see? We've got 1, 2, the 3 variables there. If you're assuming delta H vaporization is constant, that's okay in certain temperature ranges and whatnot, but it's obviously a little different at room temperature versus the boiling point of water. So, for example, the types of questions I can give you the 2 different pressures, 1 temperature, and I can give you delta H vap and say, hey, what's the boiling point at some pressure? Right? And a nice trick is you'll always have a P1, T1, because you always know if you take sea level, where the pressure we're going to assume is exactly 1 atmosphere, you know the boiling point of water, we're going to put exactly 100 degrees Celsius by definition. Woo, right? But you can look at data tables and whatnot and just find 2 different values there. Or I can give you 2 different temperatures, right? And one of the pressures and say, well, what would the pressure be at that particular temperature? Right, or that boiling point. Or you could actually say, hey, you know what? If I give you the 2 pressures, 2 temperatures, we could calculate the delta H vaporization. Right, we could over that temperature range. R, of course, is a constant, the 8.3145 joules per mole Kelvin, because we're dealing with energetics. Delta H vaporization is typically kilojoules per mole, so you're going to need a joule to kilojoule conversion in there. So let's do one example of this, show you how to track. The math isn't challenging, but it's tedious, right? Especially tracking the uncertainty. But like I said, 3 different types of equations. Solve for a temperature, solve for a pressure, or solve for delta H vaporization. And typically, you're given the value of delta H vaporization, and you're either solving for a pressure, which I think is easier, right? You do the E to the, right? If you look on your calculator, right? So there's my natural log button. Do you see the second function? Base E. Solving for temperature is a little bit harder because it's in the denominator, so you got to isolate it. It's a big pain in the butt. Got to move this over, and then you got to inverse your answer. You're like, oh, this is taking forever. So let's do one example of this. Make sure you do all your homework and look at all the different examples so you can see the 3 different ways of doing this. Solving for a temperature, how to work through the math. Solving for the pressure, how to work through the math. Or solving for delta H vaporization, which is easy peasy. Right? Let's do one. Here's a common type of question you might get. What is the vapor pressure of water at 40.0 degrees Celsius, or any temperature, really? Now, the assumption here is I could just look on a vapor pressure table, like there it is right there, right? But I'm not, if I didn't give that to you in a test, or if you had a vapor pressure curve, you could just eyeball, that temperature over and look at the value. All right, saying we don't have vapor pressure curves or data tables, all right? We got to use the Clausius-Clapeyron equation. A couple of assumptions we're going to have to make here, right? So the delta H vap is given to you in this, and that's the value at 25 degrees Celsius. And the reason I chose that, it's a little closer to 40. So if our answer is off a little bit, it's because we're using the value at 25 degrees Celsius to solve for something at 40 degrees Celsius. But it'd be better than using the value of 40.7 kilojoules per mole at 100 degrees Celsius, because 40 is closer to 25 than it is to 100, right? So the true value of vapor pressure is probably going to be in between. So if we use 40.7 here, the true value is probably going to be in between the values we got. So don't freak out if our pressure is different than on the data table a little bit. But if I gave you a more accurate value for that at 40 degrees Celsius, that would be better. And I'll provide those for you. But if you ever run into it where that's not provided, then you can say, well, is it closer to 25 or closer to 100, those kinds of things. So that's assumption number 1. But I gave you that value, so let's just use that value. Let's think about this problem, right? Using the Clausius-Clapeyron equation, so we need to identify P1, T1, P2, and T2. Right on? Well, we're solving for the vapor pressure at this. That's our final, well, you could call that T1 or T2. It doesn't matter, right? But since I'm solving for it, I'm going to call that T2. So let's let T2 equal 40. Now, we need these in Kelvin to do it, correct? So let's figure out what that is in Kelvin. So let's take 273.15 plus 40.0. That puts us good to 1 decimal because that's exact. 313.15. Right, I'm just going to convert that to Kelvin now because I need that. Now, it didn't give us the units there, so it doesn't matter. You could do it in atmospheres, millimeters mercury, whatever you want, right? It doesn't matter. Let's do it in millimeters mercury for kicks and giggles. Now we need P2. That's what we're solving for, right? So let's let, so we're solving for P2. Right, so we'll call that T2. We're solving for the pressure at that, so that would be P2. We're not provided a P1 and T1, are we? No, panic on the test. What do I do? If you're given a reference pressure and temperature, great, right? Or if you're given a table, you can look at one on a table. But if you're stuck like this on a test, you're like, I'm missing information. Oh my gosh. You always know the value of water at its boiling point by definition, right? The normal boiling point, right? 1 atmosphere or 760 millimeters mercury or 760 torr is 100 degrees Celsius. We're going to assume those are exact. Okay? So let's say this. Let's do this in black. So P1 and T1 are not provided. So use the normal boiling point of water by definition, right? Now, if I gave you something other than water, we wouldn't be able to do that. I don't expect you to know the normal boiling point of ammonia or some, tetrachloro, methane or something like that. So, but for water, we do have that as a reference point. So we're going to let P1 equal 760 millimeters mercury. We're going to call that exact. Or you can do 1 atmosphere there. And then we're going to let T1, that would be the normal boiling point, which would be 100 degrees Celsius. So if we add 273.15, we get 373.15 Kelvin. So this took a little bit of thought, a couple assumptions, right? We're using the normal boiling point of water as our initial reference point at P1, T1, and we're using the delta H VAP that we know that is closest to that particular temperature, assuming it's constant in that temperature range. But again, expect a little bit of error from that. So go ahead and write down the Clausius-Clapeyron equation, plug in P1, T1, T2, delta H VAP, we know R, 8.3145 joules per mole Kelvin. That is not exact. And you only have one variable now. That's P2. Solve for that. And again, we could have done atmospheres, but the vapor pressure table we can compare when we're done. This is in millimeters mercury, which is the same as torr. So that way it gives us a better comparison. Have at it, track it in steps, and then I'll walk through it slowly. All right, so for the first step, we're going to plug in our data, right? So here's the Clausius-Clapeyron equation, depending whichever one you use, doesn't really matter. And again, if you identified P1 and T1 and P2 and T2 opposite what I did, you'll still get the same answer. It's okay, so don't freak out. Which one's P1? As long as you keep P1 with T1 and P2 with T2. It doesn't matter which one you call which, all right? So P2 we're solving for. P1, right, that was our reference state of the normal boiling point of water. So 1 atmosphere or 760 millimeters mercury. That was the delta H vaporization provided, right? That's R. T2, right? That was the reference point. No, that's what we're solving for, right? So that was the 40.0 degrees Celsius converted to Kelvin. And then T1 was the normal boiling point of water, which is, so this is considered exact. And that's considered exact. Right now. Now, hopefully you can see an issue here. Kilojoules and joules aren't going to cancel out, so we're going to have to do a joule to kilojoule conversion in there. But what we want to do to track uncertainty, we got to get this temperature term, right? Because there's a subtraction in there. We're limited by the largest absolute uncertainty, aka fewest number of decimal places. So let's do the divisions first. We'll do 1 divided by that. That'll be good to 4 sig figs. 1 divided by that, that's going to be an exact answer. And then we're going to have to subtract those. Then we can take care of the rest of this. You see all the steps. And then we'll do the multiplication division. Then we're going to do the E to both sides, a whole different set of rules. Then we're going to multiply that over. Oh, this is like a 4 or 5 step problem. So do me a favor. Calculate the inverses of those. Put them in there. And let's take care of that first. We don't have to mess with this yet. So do that for me. See if you can get this term in parentheses to the proper uncertainty. And I'll do it. I'm going to pause. It's going to take me a second. Ready for the next step? We'll just take it one step at a time. So the first thing we're going to do is we're going to do these divisions here. Okay. So I left this term alone on the left-hand side. What I did is I added the kilojoule to joule conversion, right? So you can see how these are going to cancel out. So kilojoules is going to cancel kilojoules. Moles cancels moles. Joules cancels joules. I'm going to be left with Kelvin there. Do you see over here? When I do 1 divided by 313.15, good to 4 sig figs, I get 0.003193. There's my 4 sig figs, 35. Inverse Kelvin. And then here, 1 over 373.15, that's exact. So I just wrote as many as I could fit. 0.00267988. My calculator, kept going, but it's not going to make that big a difference. Inverse Kelvin. So now I'm going to do this subtraction here, limited to 1, 2, 3, 4, 5, 6 decimal places. Right? So do that, and then we're going to multiply this by that and see how the Kelvin's going to cancel the inverse Kelvin. And that's going to give you a unitless term, which we need for the logarithm. Boom! Okay, do that subtraction for me to 6 decimal places. Write that number in there. You can multiply these out, so I'll get those 2 terms I need to multiply. Then we'll worry about the anti-log. Oh, do the next step. All right, did you get the next step? Okay, so we haven't even touched the left side yet. Ultimately, we're going to isolate P2 and solve for that. So if I take the negative 44.0 kilojoules per mole divided by the 8.3145 joules per mole Kelvin, set up in a unit line equation, I like to be able to see how, so when you divide by something, you just flip the inverse and you can really see how the units cancel out. And then convert the joules to kilojoules. Everything cancels out except Kelvin. Thousands exact. We got 5 sig figs there, 3 in the delta H, so I get 3 sig figs here. So I get this whole term here. I get negative 5,291.9 Kelvin with a dashed line after the third significant figure. So when I take these 2 numbers, right, and subtract them to 6 decimal places, I get 0.00051346 inverse Kelvin, good to 1, 2, 3, 4, 5, 6 decimal places. Now that leaves me with 3 significant digits. So I just added the next step. Let's solve for the term on the right since we know everything. So if I take the negative 5,291.9 Kelvin times 0.00051346 inverse Kelvin, good to 3 sig figs, I get negative 2.7171, good to 3 significant digits. You tracking the uncertainty here? Welcome to the world of chemistry. We're the only ones who do it. Now I've simplified the whole right-hand side to negative 2.7171, good to 3 significant digits. And it's unitless. Yay for logarithms. So now I have to do the anti-log of the natural log, which is e to the x. So I'm going to take e to the x of both sides. See that? And then I'm going to move the 760 millimeters mercury over. Do that for me. I'll pause it and set it up for you. That should have been an easy one, right? So take e to the x. That cancels out the natural logarithm, just leaving you P2 over 760 millimeters mercury, which is our defined P1, right? And then we're going to take e to the negative 2.7171. So we need to punch that number out, but we need to know how to track the uncertainties. So if you remember, the oversimplified way is when you take the anti-log of something, e to the x or 10 to the x, the number of decimal places, the number of technically significant decimal places will be the number of your sig figs, right? This is the numbers to the right of the decimal, I think it's called the mantissa. Is that right? Mantissa. Sounds like a supervillain. I am the mantissa. Right? So I have the 2 significant decimal places there. So when I go e to the negative 2.7171, I will get 2 significant digits in my answer. Punch that out for me real quick. Let's see what we get. So where's my so I got to do the second function natural log there. So second function natural log gives me the e to the, and then I'm going to do my negative 2.7171. So I get 0.066066068. Blah, it goes forever, but I can only have 2 significant digits, right? Whoops, I lost my cap. Right, so let's solve for that. So I get 0.066. There's my 2 significant digits, right? Because of the 2 significant decimal places there. 0.06606. And that's unitless, right? Oop, I don't know if you can see that with the glare. Probably not. Find my cap. We're almost done, gang. One more step. Now, obviously, if I'm on my own, I would breeze through that a lot faster than that, okay? But I wanted to show you every step to see, because I see so many of my students, they know how to get the math, but they can't get the answer that I got. They're so, like my homework, how did you get that answer? Because they skipped a step, got sloppy with their math. That's one of the biggest issues I see. People coming out of K-12 education, they're sloppy with their mathematical processes. They're just trying to get to the answer as fast as you can. That's not what a chemist does. Chemists have to take it smooth and slow and careful. Very systematic, because we're tracking not just the math, we're tracking uncertainty and units. See how I tracked all the units? I had the division there. I had the subtraction there. I had the multiplication here. I have the e to the x here. And then the last step, I got the 7. There's 5 different steps in this. So now just multiply through by 760 for our last step. So P2, right? Multiply both sides by 760. And it happens to be in millimeters mercury. Now, if you had done this as 1 atmosphere, you'd get an answer in atmospheres, right? But I didn't, and both are okay, because in the original problem, I didn't specify what unit. But we're going to compare to the table in a second, and that's in millimeters mercury. Thus, the reason I picked it. But on an exam, I would either specify the pressure unit, or I would accept both for the answer. So what is this? 0.066. So I have, this is exact by definition. I've got 2 sig figs, so my answer is going to be good to 2 significant digits. Let's pop this puppy out. I like to do a lot of my problem. When I'm lecturing live, I don't have answers. I just make up a problem. Sometimes I have the class give me stuff. Give me a pressure, give me a temperature. And I work on it live. I don't know the answer ahead of time. So students can see me work my brain in real time through the steps. And I make mistakes sometimes. So shoot me an email if I screw this up. So 760 times 0.06606. I'm going to be good to 2 significant figures. So I get 50.2056, right? But I can't draw. I only need the 50. But let's do the non-rounded intermediate values. So 50 point, oh, there's a dashed line there, right? 0.20, and that'll be millimeters mercury. So when I round this, it's closer to 50 than 51, so that just stays as 50. We need the naked decimal there to make that trailing 0 significant. Right, so we would predict at 40.0 degrees Celsius, the vapor pressure of water would be 50 millimeters mercury. Now, of course, our delta H vap was an assumption, so let's take a look on here at 40. This is the table. Where is 40? So it predicts 55, what is that, 55.6 millimeters mercury at 40. So we're a little bit low. If we had calculated this with the 40.7, I think I had done that separately or something like that. What did I get? So if I did that with 40.7 at the 100 degrees Celsius value, I got 61-ish, what about 61.5? And so we're kind of in between, right? True value is 55, so that makes about sense there. So a little bit error because of our delta H vap, but that's how you use the Clausius-Clapeyron equation, right? So practice it. Practice some that where you're solving for the temperature. Do some other ones where but this is how you would set up an equation in these steps to track uncertainty solving for one of the pressures, either P1 or P2. Doesn't matter, right? But the mathematical process for solving for one of the temperatures is very different. Be methodical, my friends. You got this. Rock and roll.